We will look at ionic compounds first. This is where electrons are transferred. We have a metal reacting with a nonmetal, and they do so by transferring electrons from the metal to the nonmetal. The metal becomes a cation, the nonmetal becomes an anion. We learned about this back in chapter 5 when we talked about nomenclature and how to write formulas for ionic compounds. This is explaining why they do what we observe that they do. So we get the formation of a cation and an anion, and then there's an attraction between those opposite charges, and that results in the ionic compound. So in Lewis theory, we can show this by just moving the dots from one atom to another. So let's look at potassium and chlorine and show the electron transfer that happens when they bond. So here's potassium. How many valence electrons does potassium have? It has 1. So potassium has 1 valence electron. And then we've got chlorine, and chlorine has how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. Both of these guys want 8 valence electrons. Potassium has 1 valence electron. If I take that electron away, does that mean it has no electrons? No. That means, here, let's write this out. Let's look at the electron configuration for potassium. 1s2, 2s2, 2p6. 3s2, 3p6, 4s1. So this is the valence electron, right? If I get rid of that, what's left? What becomes the valence electrons?
3s and 3p.
We have 3s and 3p, and that's a total of 8, right? So when we take this one guy off, underneath is a full level. That's 8. That's a noble gas electron configuration. That's the same electron configuration as argon. That's 8 valence electrons. That's a good thing. And so potassium's like, well, good. If I could just get rid of this one extra electron, it's like my mom made me wear a sweater. If I could just take this thing off, I would look like the cool kids who are freezing to death in their shirt sleeves, right? If I could get rid of this electron, I'd look like argon, and then the girls would like me, right? Because underneath is this. Now, in these Lewis structures, we don't show anything that was underneath. So what we're going to show is we're going to show potassium getting rid of this electron. And then we're going to show him, he's going to look naked. But he's not really. Okay, he just took his sweater off. So this electron, what color should I use for this? Maybe red. See if red shows. This electron is going away. We're going to give it to chlorine over here. Because chlorine's got 7, and chlorine's thinking, man, if I could just get one more electron, then I'd look like argon, and I'd be really cool. And I get 7, I just need one more. And here's potassium trying to get rid of 1. So that was gone. What does that do to the charge on the potassium atom? It gives it a charge, right? It's short an electron, now it has a positive charge. This chlorine gained an electron. What does it do to its charge? It causes it to be negative. What we usually do is we put a bracket around this and put the negative on the outside. I think so it doesn't get lost in all the dots, just to be clear. So potassium had 1 valence electron it needed to get rid of. Electrons don't just disappear. They have to go somewhere. If an atom is going to get rid of one of its electrons, it has to find someone to take the electron. So the electron is taken from potassium and given to chlorine. The result is you have a potassium ion and a chloride ion, opposite charges, and then they're attracted to each other and they form an ionic compound. Any questions? The result is the chloride ion has an octet. Potassium lost its only valence electron, but underneath, the previous shell, which was part of the core electrons, becomes the valence shell. And we do brackets and the charge on the outside. Important, in mastering chemistry, the charges are shown, but the brackets are not shown. See that? The brackets are not shown. Please do not text me and ask me where the brackets are on mastering chemistry. There's no button for brackets. I know this. I'm telling you. It won't let you do brackets. I find it frustrating too. No brackets. Okay, no brackets in mastering chemistry. Did you get that? No brackets? No brackets. Just the charges. Somebody's going to ask me. Write the Lewis structure of the compound NaBr. Well, there's different ways to do this. There's Na, and here's Br. Let's think of it in terms of the atoms first. So how many valence electrons does sodium have?
1.
It's got 1 because it's in group 1A. And how many does bromine have? 7. 1, 2, 3, 4, 5, 6, 7. So what's going to happen is if we move that electron over there, what does that do to charges? This is positive. There's the brackets that mastering chemistry will not let you put in, and a minus. This is the Lewis structure for the ionic compound sodium bromide. It shows the different ions and their charges, and the anion has a full octet of electrons. We don't show the underlying electrons from the sodium. Some students find that disturbing. I think it would be confusing if we had dots appearing that weren't there before. And so we just kind of understand, okay, it had 1 and we moved it over here, and we understand that underneath it is fully clothed, okay? It's got electrons under there, and so we're not going to worry about it. Any questions? Lewis theory helps to predict correct formulas for ionic compounds. Let's do barium fluoride. So here's barium. How many valence electrons does barium have? It has 2. And then we've got fluorine. How many valence electrons does fluorine have? 7. 1, 2, 3, 4, 5, 6, 7. I know it says BAF2. I'm just going to look at these 2 guys. So barium wants to gain 6 electrons or lose 2? Lose 2. Because that's the shortest route to getting 8. If it gained 6, it would also have 8, but that's just too hard, right? It's going to go the easy way. And the fluorine wants to gain 1 electron. So fluorine comes up, man, I'm just short an electron. Could you give me one of yours, please? And barium says, oh yeah, I'd be happy to help you out. I'm trying to get rid of 2 electrons. You want 2 of them? And fluorine says, no, just 1, thanks. And so, you like how my atoms talk to each other? It's pretty stupid, isn't it? So now fluorine's great. Fluorine's happy. So we can put brackets around him, and he's got a minus charge. And what charge does the barium have right now? It's got a +1. Is barium happy? No. Barium got rid of 1 of his electrons. He's happier, but he's not happy yet. And that's why we need a second fluorine. So enter fluorine number 2. And the other fluorine also has 7 valence electrons. Hey man, can you give me an electron? Oh, I thought you'd never ask. And so let's take this electron, and we're going to move it over here. Now the fluorine's happy. It's got a -1 charge. And what's the charge in this barium ion now? It's a 2+. So we have atoms working together. They don't actually do that, but this is chemistry land, right? We can make up scenarios for them. They're working together, they're sharing, they're transferring, they're arranging things so that everybody can be happy. Wouldn't it be nice if people could do that? But that's as far as I go as in terms of touchy-feely stuff like that. Any questions? So when you're drawing a Lewis structure for ionic compounds, you're going to show the cation with its charge, and the anions are going to end up with octets of electrons, brackets, except on mastering chemistry, and their charges on the outside. If it's showing 2 of them, you need 2. Yes?
If they gain 2, it would be 2 minus.
Right. Yeah, if this was something else like oxygen and it gained 2 electrons, then it would have a 2- charge, and it would have gotten 2 electrons from the barium. Use Lewis theory to predict the formula of the compound that forms between magnesium and nitrogen. Well, magnesium. I'll put him in the middle. How many valence electrons does magnesium have? 2. So 1, 2. And nitrogen. I don't know, I like lavender today. Nitrogen, how many valence electrons? 5. 1, 2, 3, 4, 5. Well, let's see what we can do. So this nitrogen needs 3 more electrons, and this magnesium needs to lose 2 electrons. So we could take these 2 electrons and give them to nitrogen. So I'll put 1 over here and 1 over there, and I took those off. Ugh, it wasn't the eraser. Took those off. Now we've got some charges going on, right? This is 2 minus. It's got brackets now. What's the charge on the magnesium? 2+, because it lost 2 electrons. Are we good? Is everybody happy?
No.
No. Magnesium's happy. Nitrogen only has 7 electrons. He's like, what? This isn't good. We need somebody else who's willing to give up electrons. So we need another magnesium. So here's another magnesium. This magnesium has 2 valence electrons. Nitrogen says, hey, give me an electron. Okay. There we go. Let's fix our charges. Because that's not 2- anymore, it's what? 3-. And this magnesium that lost 1 electron has a +1 charge now. Now we have 1 happy magnesium ion and 1 happy nitrogen ion, but we have an unhappy magnesium ion. So this magnesium needs to find a nitrogen atom to give its electron to. So here's another nitrogen atom. Nitrogen atoms. 1, 2, 3, 4, 5. So we'll take this electron and give it to the nitrogen. And now this magnesium ion is happy. How about this nitrogen ion? Not so much. We need some brackets on him because he's got a charge now. He gained 1 electron. He's got a -1 charge, but he's not done yet. He's going to look for someone to give him electrons. Well, where there's 2 magnesium atoms, there's probably another one. So let's bring in another one. This is one of those group effort compounds. So here's another magnesium atom with 2 electrons. And this nitrogen needs how many more electrons? 2. We thought this was never going to end, huh? So we take these 2 and give it to this nitrogen, and then he'll have 8. So we've got the electrons moved. Now this has a 2 plus charge, and this has a 3 minus charge. So when we have 3 magnesiums and 2 nitrogens, they can shift the electrons around and make everybody happy. What's the formula then? Mg3 N2. We learned how to do that from charges because we learned that magnesium has a 2 plus charge and nitrogen has a 3 minus charge, and we did that crisscross thing. And we learned to predict that way, but that didn't explain why it did that. This explains why magnesium and nitrogen do that. You got to admit that's a little bit neat. A little bit, just a little bit. I'm not going for much here. Any questions?